Today will be a continuation of a video I made a couple weeks ago called Fibonacci Sequence and Golden Ratio. I will be going into more depth about the golden ratio and how it relates to the Fibonacci sequence as requested by user Calculus. If you like the video, make sure to hit that like and subscribe button. As mentioned in my previous video, the golden ratio is defined by a ratio of a plus b over a that is equal to a over b, which also we like to call phi. Now this ratio shows the relationship between two squares or two rectangles of lengths a and length b, and how when we add these together to get a plus b, the ratio between a plus b, this total length, over a, just the length of a, is equal to the length of a divided by the length of b. This golden ratio number is found to commonly be 1 plus the square root of 5 over 2. So this is the number that we arrive at. It's technically plus or minus, so it's plus or minus 1 plus or minus the square root of 5 over 2. We like to think of the minus version as the conjugate, so I'll just be focusing on the plus version. This ratio was studied over many years by many famous mathematicians, including Kepler, Euclid, Roger Penrose, and even Fibonacci himself. This golden ratio has been proven to be irrational. Because simply this number, in order for it to be rational, we can kind of pull out, we can think of this as 1/2 plus root 5 over 2. Now, this would imply that if the golden ratio was rational, that would imply that the square root of 5 is rational, which is not true, as the square root of all non-square natural numbers are irrational. There's also a very interesting pattern that arises when examining a simple continued fraction for the golden ratio. It is observed that the conjugate root to the minimum polynomial of x squared minus x minus 1, we kind of have the golden ratio in this sort of form as seen in my previous video. We can get this sort of relationship. So phi equals 1 over phi plus 1. If we expand this out by noting that phi equals this whole thing, we can just say that, well, phi equals 1 over this whole thing. 1 over phi plus 1, right? Because we have phi, we have 1 plus 1. Well, if phi equals this whole thing, we replace the phi down here with this, right? This box replaced with this box, right? Because phi equals this whole thing. So if we do that, say we do it again, well, phi also equals 1 over phi plus 1 plus 1. And then there's plus 1 here. Okay? Oh, wait, no, that's not plus 1. So then we have 1 plus 1 over 1 plus 1 over 1 plus 1 over phi. We can do this on forever and ever until we get something that looks like this. 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over and so on and so forth. You kind of get the idea. We got 1 plus 1 over 1 plus 1 over 1 plus, we have this long, and this continues on forever. This goes on forever and ever. If we observe the convergence of this fraction, which are just rational approximations of this continued fraction that goes on and on forever, we have the first one is just 1. I'll just represent it as 1 over 1. The second one is 1 plus 1, which is 2 over 1. The third, we have 1 plus 1 over 1. No, 1 plus 1 over 2 is going to be 3 halves. And our next one is going to be 5 thirds. Next one will be 8 fifths. Next one will be 13 eighths. And the last one I'll do is 21 thirteenths. So this might seem like a random assortment of fractions, but if we look at it, 1 and 1, well, let's write out the Fibonacci numbers. The first one is 1. Next, 1, 2. If we add 2 and 1, we get 3. 2 and 3, we get 5. 3 and 5, we get 8. 5 and 8, we get 13. 8 and 13, we get 21. I'll go this far so that you can see 1 and 1, 2 and 1, 2 and 1, 3 and 2, 3 and 2, 5 and 3, 5 and 3, 8 and 5, 8 and 5. And this goes on forever until we eventually reach the actual number of the golden ratio, which is found to be about 1 plus root 5 over 2. So when we approximate the golden ratio using 1 over... When we approximate the golden ratio using this formula, let me write that better. In this continued fraction, we get ratios of only Fibonacci numbers. Isn't that interesting? So this is one of the few ways that the golden ratio and Fibonacci numbers are connected. As a last point to this video, I will also admit that there is a mistake in the first Fibonacci sequence video. If you spotted it, kudos to you. I claim that the golden ratio numbers follow the pattern of the Fibonacci sequence by changing the initial b value. Well, that would imply that phi n plus or equals phi n minus 1 plus phi n minus 2. That would imply that this is true, which is not true. I apologize. I did write the formula correctly, which is phi to the power n equals phi to the power n minus 1 plus phi to the power n minus 2. These are powers, not necessarily numbers in the sequence of the golden ratio. But what is true is that this formula is true. This one is false. Okay. What is true is that when we take a power of the golden ratio, it is equal to the golden ratio of the previous power plus the golden ratio of the next previous pattern, the previous one after this one. So these do follow the pattern of Fibonacci recurrent or recursion, just not the actual values themselves. There's only one Well, technically 2. This is the only value of the golden ratio. There's not multiple values. But you can take the powers, and they do follow this pattern. Thank you so much for watching. If you enjoyed this video, make sure to hit that like and subscribe button, and leave a comment below of what topic you'd like to see next. This is Dylan signing off. Hope you have a good day, and see you in the next one.